into rational exponents. And so we had left off here with question letter F, where we were having a look at the square root of 8 to the power of x plus 2 is equal to the cubed root of 32 to the power of x minus 3. Okay, first thing we want to do is go ahead and write the square root of 8 as 8 to the power of 1/2, all to the power of x plus 2. The cubed root of 32 we can write as 32 to the power of 1/3, all to the power of x minus 3. Now, you remember from last time that 2 to the power of 3 was equal to 8, and 2 to the power of 5 was equal to 32. And so if we have 2 to the power of 3 to the power of 1/2, all to the power of x plus 2, that'll be equal to 5 to the power of, not 5, 2 to the power of 5 to the power of 1/3, all to the power of x minus 3. Now at this point, the bases are the same, so we can work with the exponents, but we'll just go ahead and simplify the exponents down a bit first. And so we have here that 3 times 1/2 will be 3/2, so it'll become 3/2 multiplied by the quantity x plus 2 is equal to 5 times 1/2, which will be 5/2, times the quantity x minus 3. Now at this point here, we can eliminate the denominators by multiplying both sides by 2. And what we end up with will be 3 times x plus 2 is equal to 5 times x minus 3. And now at this point, we can go ahead and just expand and simplify down and see what we get. So we'll multiply the 3 onto both terms inside of the bracket for x plus 2. And what we end up with will be 3x plus 6. 5 multiplied onto both terms inside the brackets will yield 5x minus 15. Let's go ahead and collect all of the x's on the left side. So we shall subtract 5x from both sides, which will give us negative 2x. We'll minus 6 from both sides, which will give us negative 21. So we have negative 21, negative 2x is equal to negative 21. Dividing both sides by negative 2 gives us our answer being 22 on 2, or if you prefer, 10.5. So again, if we wanted to go ahead and check that, we could insert that back into the original, but for now, that'll be okay. Okay, 2 left on this lesson before we get caught up to today's material. We have 1/4 to the power of x minus 2 and 1/8 to the power of x plus 1. So again, these are going to, we can either work with both with negative exponents, but remember, if we have negative exponents, then we're going to need to just divide by a negative later. So let's work with a base of 1/2. 1/4 is going to be the same thing as 1/2 to the power of 2 times x plus x minus 2, and that'll be equal to base. And now instead of 1/8, it'll be 1/2 to the power of 3 multiplied by x plus 1. And again, at this point, we can work directly with the exponents. And so we end up with 2 multiplied by x minus 2 is equal to 3 multiplied by x plus 1. Multiplying out the bracket, 2 times x minus 2 is going to be equal to 2x minus 4. 3 multiplied by x plus 1 will give us 3x plus 3. We're going to collect the x's on the right side this time, because if we take 3x minus 2x, that'll give us just a regular x. If I take negative 4 minus 3, that'll give us negative 7. So our resulting answer will be negative 7 is equal to x, or as most people probably prefer, x equals negative 7. Lastly, but not leastly, seemingly a lot more difficult of a question, but again, not too bad. We have 5 to the power of x multiplied by 5 to the power of x minus 1 is equal to 125 to the power of x, to the power of 4x, sorry. And so if you notice, in this case here, we seemingly have 3 base terms to worry about. And so let's go ahead and do that, and perhaps our next steps will become a bit more obvious. So 25 to the power of x is the same thing as 5 to the power of 2, all to the power of x. 5 to the power of x minus 1 looks okay, so we'll just write that down. And 125 is the same thing as 5 to the power of 3, all to the power of 4x. And so at this point here, let's go ahead and simplify down the exponents. 5 to the power of 2 to the power of x is 5 to the power of 2x. And we still have a 5 to the power of x minus 1, so we'll put that right beside it. And 5 to the power of 3 to the power of 4x will be the same thing as 5 to the power of 12x. Now the reason, and again, for some of these questions, if you're like, oh, I'm not sure how we proceed, you proceed down the normal path as much as possible in hopes that next subsequent steps become easier to see. Now, if you notice here, we have 5 to the power of 2x multiplied by 5 to the power of x minus 1. Our exponent rules say that if we have two powers with the same base being multiplied together, we can just add the exponents. And in fact, that's what we're going to do here. And so we're going to have 5 to the power of 2x plus x minus 1 should be equal to 5 to the power of 12x. 2x plus x is going to give us 3x. And so we're going to so we saw that 5 to the power of 2x multiplied by 5 to the power of x minus 1 becomes 5 to the power of 3x, which is equal to 12x. From here, we can just equate the exponents. So we have 3x minus 1 is equal to 12x minus 3x from both sides. We get negative 1 is equal to 9x. And if we divide both sides by 9, we get x is equal to negative 1 over 9. Okay, again, a lot more complicated, but easily we can check to see if this is the case by substituting in, but we'll trust that that's correct. All right, let's get started with today's stuff. Now, this is another one of these review topics where this course talks quite a bit about the idea of functions. And so I wanted to visit the topics that will be necessary. We're not going to study functions in depth, but I wanted to give you kind of a survey of what we're going to be doing related to functions that you should be aware of that will come up in this course. So specifically, topics that are that we're going to review, if you've seen it before, or review for the purposes of making sure we understand the lesson, will be function notation, domain, and range. The lesson portion starts immediately with exponentials and their inverse, so we'll get to that today. So let's have a look. So why do we care about function notation? So we're going to consider this equation. Y is equal to 2x plus 5. So we know from previous studies that this equation becomes a line. So you can see here I graphed what this looks like, and this happens to be the equation y is equal to 2x plus 5. And so the idea behind function notation is that we were interested in, say, for example, or why we want to do this, is to solve this problem. Suppose we are interested in two particular points, x equals negative 1 and x equals 2. Okay, if I wanted to figure out the value of y, I would be writing let x equal negative 1 and solve for y, in which case we'd have y is equal to 2 times negative 1 plus 5. So 2 times negative 1 is negative 2 plus 5, which means y is equal to 3. So this point becomes the coordinate negative 1 comma 3, which I've mapped here on the right. Similarly, if we wanted to type in x equals 2, same procedure as before, we'd say y is equal to, now instead of 2x, it becomes 2 multiplied by 2 plus 5. 2 times 2 is 4 plus 5, and so y would be 9. So if x equals 2, y would equal 9. So this becomes the coordinate 2 comma 9, which you can see is on our graph. This is pretty clunky notation in general. So whenever we wanted to evaluate a point, it was always a little bit awkward to do this because we needed to always state the sentence, let x equal this, and then go solve for some value. The idea behind function notation is that we instead say, instead of y is equal to 2x plus 5, we now say f of x equals 2x plus 5, where f in this case stands for function, and x is the variable we care about. That's in the equation. So these two things become together. It's worth noting that y is exactly the same thing as f of x. And so the lesson will periodically write y and also periodically write f of x. And just understand, for the most part, those are interchangeable with some caveats. And so f of x is treated as just a single term. That's it. So it's kind of like how we said that surface area might become like SA or volume was V. Functions are just f of x, and that's one term. And so how does this work? So f of x is the way we describe something. And if we were interested in the points x equals negative 1, x is equal to 2, we would write it as the following. So if we have f of x equals 2x plus 1, f of negative 1 would become 2 times negative 1 plus 5, which becomes negative 2 plus 5, which is 3. And if f of 2 would equal 4 plus 5, which is equal to 9. And so previously, we saw that the point x comma y became negative 1 comma 3. This will now be the point x comma f of x. Okay, so instead of x comma y, we call it f comma f of x. So in terms of our chart up here, we know that the x-axis was the horizontal one and the y-axis was the vertical one. The x-axis stays the same, but the vertical axis we could now call, say, f of x instead. So this again is the point. Why does this matter? Well, it's to make things a lot easier, such as the following. So for example 1, we're going to use function notation. And so given f of x is equal to 4x minus 1, g of x is equal to 4x squared minus x plus 1, and h of x is equal to 5 times 3 to the power of x, we can now do the following. F of negative 1. So all that means is we are going to take our f of x function, and wherever we see an x, we're going to replace it with a negative 1 in brackets. So this becomes f of negative 1. So 4 times negative 1 is negative 4 minus 1, which becomes negative 5. Okay? And this notation just is replacing let x equal negative 1 and solve for y. So this notation, the purpose of it, in this case, is to help us save time. So if we are given g of x is equal to this quadratic, g of 2, wherever we see an x, we're going to put a 2 instead. Okay, and we can use our calculator for this one, I suppose. Four bracket 2 squared minus 2. And again, as a reminder, I'm using the Desmos scientific calculator that you can see at the top of the screen here. And when we type this in, we end up getting 4. For our purposes, it's enough to show that if g of x is this quadratic, g of 2 is this is what we're typing in, and we get our answer. Like, we don't get marks for showing all of our individual steps. You get 1 mark for saying, hey, this is what I'm trying to evaluate, and then whatever you get at the end is good. But why stop there? What about h of 2? Well, h of 2 is this exponential. So if h of x is equal to 5 times 3 to the power of x, then h of 2 will be equal to 5 times 3 to the power of 2. Following PEDMAS or BEDMAS, 3 of 2 is 9, and 5 times 9 is 45. Okay, so all we did was replace the x, which in this case was the exponent, with the 2 that we cared about. D, we got g0, or g of 0. And I should mention that the way to pronounce this is we would call this g of 0. And I suppose I should probably type out the word 0 for us. I'll put this in quotations, or we say g at 0. I will often default to calling it g of 0 instead. And all it means is what's the value of y when x is equal to some value. Okay, so g of 0, so let's go ahead and figure that one out. That'll be equal to 4 times 0 squared minus 0 plus 1. So g of 0 would just be equal to 1. F of 10 4 times 10 minus 1. 4 times 10 is 40 minus 1, which is 39. And h of 0 would become 5 times 3 to the power of 0, but anything to the power of 0 is equal to 1, and will be our answer. I mentioned this because, again, this lesson just kind of introduces this notation. And because of just sometimes how it's typed, they might write it as capital f of x or smaller case f of x. These are the same thing. And then from there, it's pretty standard to call most relations f of x equals something. It's just that if a particular question has more than one letter, say like this one does, they'll have f, g, h, I, j, k, so forth, or as well as like some other ones like c and r. Okay, so just note that one part of the notation is just replacing y with f or g of x, so that it's a little bit less clunky notation when we want to start evaluating things, such as in this example. There's a more technical definition that we're going to talk about briefly. A function, by definition, is a relationship between two variables, in our case, x and y. It can actually extend to more dimensions, but for now, we'll just consider two variables, where each x value goes to only one y value, which sounds like something we've been always doing, but which is fair, but not always true. So let's have a look at two examples that are similarly related. So on the left side here, I have a function. Y is equal to x squared. This is a standard quadratic function. These are ones that you studied last year and potentially the year before, but they're just a parabola opening upwards. If I were to insert the standard array, -2, -1, 0, 1, 2, into the function itself, I end up with y values of 4, 1, 0, 1, 4, respectively. And we map out getting this particular U shape. So again, very standard. This is the quadratic base function. However, on the right side, I have the relation, which is not a function. X is equal to y squared. So 0 goes to 0, 1 goes to 1, but 1 also goes to -1, 4 goes to 2, and 4 goes to -2. So the problem with this is that when I say look at the value of x equals 1, we can see it only goes to one answer, say 1. And if I look at the value x equals 2 for the quadratic, it only goes to one value, 4. For the relation, the problem I'm running into is that when I look at the value of, say, x equals 4, there are two answers it could be. And even if, say, I wanted this value in between, say 2.5, it could be one of two answers. So this is not a function. This is what we call a relation. All functions are relations, but not all relations are functions. So with this particular relation is actually just a tipped over quadratic. So it has what we call quadratic structure. Okay. And so that is not a function. So and all it takes for something to be not a function is that you have an x value that can go to more than one y value. It only has to happen in one spot. As soon as that happens, it's not a function anymore. This is the part where this is a little bit more detailed for functions that will come up sort of, but I might as well mention it now in detail, just in case somebody wants to review this later. Okay. So we're going to determine which of the following are functions. And if there are functions, I'm just going to label it as an F. So here, first one, we have the equation x squared plus y squared equals 25. And you can see that this maps out a circle. And so the problem is, if I look at, say, x equals 0, my answer could be 5 or -5. So this is not a function because I have two answers for that. When I look at, say, 1, it can go to two values, or -1. So therefore, it's not a function. Letter B, we have y equals x to the power of 3 minus 5x. And again, it's a little bit of an unusual shape. We actually haven't seen these before. We're going to be studying these next week, I believe, or perhaps on Thursday. It's a little bit of a, kind of looks like a little bit of a wave, but if you notice, if I look anywhere along the curve, each x value seems to only go to one y value. So here, this is a function. That's it. Question C, we have y equals 3, just a flat line. And actually, this is a function because no matter where you go along the x-axis, that only goes to one y value. D, we have x squared minus y squared is equal to 1. And so you can see kind of cuts out this hourglass figure. And we have the same problem as before. So if we have a look at x equals 2, that seems to go to two values. So that's not a function. I've got a table of values for E. We've got our x values are 1, 2, 3, 4, 5, and our y values are 7, 10, 13, 16, and 19. And in truth, all I saw were that my x values were 1, 2, 3, 4, 5. That's already enough information for me to know that that's a function, because if all the x values go to the same y value, then we know it would just be like the graph from above, which was a flat line, or a flat horizontal line, I should say. However, in this case, this happens to map out a line of some kind, and we don't care about that because all the x values are different and all the y values are some number. Doesn't matter what they are. And we're going to be in about 3 or 4 weeks or so. And so we have kind of a wave here. And so this is what we call a sinusoidal function. So basically it just kind of goes up and down forever. But importantly, we can see that each x value only goes to one y value. So this will be a function. Okay. So if you have x values that go to only one y value, function. If you have x values that go to more than one y value, not a function. The last big component of this is the idea of domain and range. So suppose we're interested in the values that a function is allowed to have. And these are given coordinates, say x comma y. The domain is the set of all values of the first coordinate of the ordered pairs. And the range is the set of all values of the second coordinates of the ordered pairs. So a more reasonable explanation of this is the domain is the values x can have. And the range are the values y can have. That's it. So we are not going to talk about the way to define, like, how do we talk about these things are. And so here we have the quadratic again, y equals x squared. Here's the table of values, and this is what it looks like. And so the question we might be interested in is, what is the domain and what is the range? What is that going to be? Well, if you have a look at this quadratic here, is there any x values that maybe we can't have? Or perhaps it's better to talk about the range first. So range means, the range in this case means what y values can we get to? So you can see here, we can put little arrows on the end of this. We kind of start at 0 and then we move upwards, wherever. So it seems like as if we can have all the positive values at 0. Can we get kind of low? So is it possible to have a y value down here at, say, -3? Oh, sorry, -4? And the answer is no. This red curve only goes up. And so it's actually impossible to have a point down here. It doesn't exist. So the way we write this, and it's pretty technical, but again, for the moment, we'll just take this as is. So we introduce a little squiggly bracket. We say y is an element of all real numbers such that y must be greater than or equal to 0. So very, very fancy notation. So let's talk about what this means. This kind of backwards e means that this is an element of, and that's a fancy way of saying what values is it allowed to have. And that r with a line through it is that symbol represents real numbers. So if you take out a ruler right now, those are all of the real numbers. There are other sets of numbers, but for our purposes, and all you need to know is that we have real numbers. Okay. Now we get a big vertical bar here. That big vertical bar means such that, and we're saying that our y values have to be greater than or equal to 0. Because you can see here, the lowest y value we have is 0 and up. Okay, so y can be anything you want, but y has to be at least as great as 0. So y greater than 0 means y must be greater than or equal to 0. And this is going to be a lot at first, but I have a bunch of I have 4 examples that follow that will kind of clear up everything for us. And then you can refer back to this as notes to help out. Just keep in mind, we have to talk about domain and range pretty much only like a couple of times in the course. Okay, but I just want to make sure that you had some handle on this for when it does occur. So when we look at range, that means on a graph, we're looking at our y values, which means we're looking at how far up or down we can go on the graph. Domain refers to the x values. And so if you notice here, for x values, I can choose 0, but then I can choose as big a number as I want, because if I have y is equal to x squared, x can be literally anything I want, and that's okay. Could I put a fraction in there? Absolutely. Could I put a decimal? Sure. Could I put 10 trillion? Yeah, that's fine. So the way we would describe that is, again, the little squiggly bracket. X is an element of all real numbers, but there's no restrictions because it can really be anything you want. So x can be anything, y kind of has to be at least as great as 0. And that's all we can do. So let's have a look at these to kind of see what these look like in action. So we're going to determine the domain and range of the following. So for y is equal to 1/4 x minus 1, this is a line. And the line just kind of continues forever, going up and down. So it will eventually get to all x values and all y values. So we say the domain D will be x can be whatever you want. You can also describe the domain and range if words if you'd like, and you'll see why we might want to do that for the next example. Similarly, the range for this line will be y is an element of all real numbers again. And the reason for that is because for the domain, if we look left and right, we don't seem to have a problem. And if we look up and down on the graph, we can kind of go as far as we can. So where do we have a problem? We actually have a problem with b. So this was that circle from earlier. X squared plus y squared equals 25. If you notice, this graph can't have any arrows on it. It just kind of forms a circle around the origin with radius 5. So this circle doesn't exist except for on this red line. And we seem to only have x values between -5 and 5. So the domain then, we would say, is x is an element of all real numbers, but it has to be between -5 and 5. So this that's what this notation means. So we have -5 must be less than or equal to x, which must be less than or equal to +5. Okay. The range has the exact same restriction. It must also be between -5 and +5. And so, for example, this equation doesn't make sense if we try to put, say, a 6 in here, because if you have 6 squared, that's already greater than 25 and doesn't make any sense anymore. So this equation is what we call a circle. For C, we have a parabola that's upside down. And so again, for the domain, we saw from before, not a problem. So the domain will be x is an element of all real numbers. But when we talk about the range, we only have a highest value. The highest value this gets to is a 3. So we say y is an element of all real numbers, but y has to be less than or equal to 3. It's the highest we can get. And lastly, but not leastly, we have this y is equal to x cubed minus 5x. And again, the domain for this, we don't really have any problems here because we can go left and right forever. And if we have a look at the equation itself, we seem to be able to type in any x value we would like. And for the range, similarly, we have y can be anything you want. So this is a little bit of the notation you can run into that the lesson may touch upon on occasion. So that way you have an idea of what these things look like. Okay, so here, what we're interested in is solving equations such as this. So here's our motivation. We are interested in solving exponential equations of the form 10 to the power of x equals 2500. However, we cannot write 2500 as a common base of 10. That is, we don't have 25 can't be written, 2500 cannot be written as 10 to the power of x easily. So it's worth noting that if we have 10 to the power of 3, that's 1,000. 10 to the power of 4 is 10,000. So it seems that the answer should be between 3 and 4, right? So if you can see on our calculator here, if you have 10 to the power of 3, well, that's 10,000. Sorry, 1,000. If we have 10 to the power of 4, well, that's 10,000. It seems that the answer to that question should be somewhere in between. So if I say, what about 10 to the power of 3.5? Oh, that's a bit better. So we can see that 10 to the power of 3.5 equals 3162, which means that the answer to this question must be between 3 and 3.5. And we can keep trying to guess this, but this guess and check is not really what we want to be doing. And so we need a more formalized method to help understand this. And so we're going to talk about the idea of an inverse. So the inverse function are a special class of functions that undo each other. And so what does this mean? So the input and output for two inverse functions are f of x is equal to 2x plus 1, and g of x is equal to x minus 2 over 2. And so these are their corresponding graphs. So when I say that they undo each other, a real-world application of this would be asking this question. If I'm traveling, say, 90 kilometers an hour, how much road do I need to have to stop safely if I slam on the brakes? The inverse of that would be, say I have 60 meters of road. What's the fastest I could be traveling to ensure that I brake on time? That would be the idea of the inverse. And so here I have the graph of what these two functions happen to be inverses of each other. And so we can see the red line kind of going up and the blue line kind of going over. And if you notice here, for f of x is equal to 2x plus 1. Here's some x and y values, 0, 1. So for the x values, we have 0, 1, 2, 3. Y values are 1, 3, 5, 7. For g of x, our x values are 1, 3, 5, 7. And g of x, they are 0, 1, 2, 3. And so if you have a look here, you might be thinking, did we just switch the x and y values and that's the inverse? And that's absolutely true. Notice that the output of the first function, f of x, becomes the input for the second function. So the ordered pair for f of x is normally x comma y becomes y comma x for g of x. So to graph a function in its inverse, a common method to graph them is to first graph the original function and then graph the inverse by switching the x and y coordinates. And what happens in this situation is that they will end up being a reflection of themselves across the line y is equal to x. So we've talked previously about vertical reflections, or a reflection in the x-axis, a reflection in the y-axis. This is a reflection in the y is equal to x-axis. So I want to apply this not to linear, which is lines. I instead want to apply this to exponentials. So the graph of the exponential function, y is equal to, say, x to the power of x, is reflected in the line y equals x, which x and y can be whatever you want. That's what this YER notation is. It's worth noting that when I write that notation, the computer writes a really nice R. Most people just end up just doing a capital R and just drawing a line through it. That's what they use to represent all real numbers. But just note that these are the same thing. And so when you graph this function in its inverse, instead of having y is equal to a to the power of x, we instead end up with x is equal to a to the power of y. So the latter one is the inverse function. Okay. And similarly, we notice that the domain of y equals x, a to the power of x, becomes the range of the second function, x is equal to a to the power of y. Now, when we talk about the inverse function, we don't like this notation of x equals a to the power of y. Looks pretty clunky. So instead, we call it just f of negative 1. So when you see f of negative 1x, this is referring to the inverse. So note that this red curve, which is what you studied before, had a horizontal asymptote at y equals 0. When we take the inverse of that, it now has a vertical asymptote instead. So we just swap those around. Okay, and notice for this particular graph, this is valid for this kind of graph will look like this as long as a is greater than, it should be a 1 here. There we go. Okay, so we're going to sketch an exponential function and its inverse. So we're going to graph f of x is equal to 5 to the power of x. So we're going to choose typical x values around the origin. Usually for exponential functions, choosing x equals negative 1, 0, and 1 is okay. In this case, we'll choose x equals 2 and x equals negative 2. So we're going to substitute each of these values. So we're going to graph the values from negative 2 to 2. And when we do this, we just say, oh, we're going to type in f of negative 2 in our calculator, f of negative 1, f of 0, f of 1, and f of 2. So f of negative 2 becomes 5 to the power of negative 2. F of negative 1 equals 5 to the power of negative 1. F of 0 becomes 5 to the power of 0. F of 1 becomes 5 to the power of 1. And f of 2 becomes 5 to the power of 2. And so typing these in, 5 to the power of 2 is just 25. 5 to the power of 1 is just 5. 5 to the power of 0 is just 1. 5 to the power of negative 1, in case you're not sure, is going to be 0.2. And 5 of negative 2 becomes 0.02. So here, this blue curve that I've already graphed for us for time purposes is going to be the exponential curve, y is equal to 5 to the power of x. Okay? And so exponential curves look like this. So previously, when you studied these are also called J curves. So if you hear the term J curve, that refers to an exponential curve. And so if I want to sketch x equals 5 to the power of y, that's the inverse. So the easiest way to sketch the inverse is actually just to sketch the original function, y is equal to 5 to the power of x, and then go ahead and swap those values. And so here, if we have y is equal to 5 to the power of x, here were the ordered pairs that I had from above. So we had negative 2 comma 0.04, negative 1 comma 0.2, 0 comma 1, 1 comma 5, and 2 comma 25. The inverse is we just switch the position of the x and y values. So now we end up with 0.04 and negative 2, 0.2 and negative 1, 1 comma 0, 5 comma 1, and 25 comma 2. So here I plotted the blue points, or at least the first 4, because I can't fit 25 on my axis down here. But here's the point 0 comma negative 2. There is going to be 0.2 comma negative 1. There's 1 comma 0, and here's the point 5 comma 1. And you can see that if I switch them. Now, it's worth noting again that these two exponentials have a reflection across the y is equal to x axis. Okay, so this is what we define and the inverse function to be, where if we, and again, for our purposes, it's good enough for us to say it, we just switch the x and y. Okay, and so we're going to sketch the exponential function and its inverse and the line of reflection. So we're going to sketch the graph of f of x is equal to 2 to the power of x and f negative 1 of x, which is the inverse of this, and the line of reflection. So first thing we're going to do is just graph the line of reflection. That's pretty easy to do. So this is just y is equal to x. There it is here. It's a line with slope 1 that goes through the origin. And so for 2 to the power of x, and so we know that the regular x values we choose are negative 2, negative 1, 0, 1, and 2. And we want to evaluate f of negative 2, f of negative 1, f of 0, f of 1, and f of 2. So 2 to the power of negative 2, 2 to the power of negative 1, 2 to the power of 0, 2 to the power of 1, and 2 to the power of 2. Leaving this as a calculator exercise, because we'll just get decimals for now to help us with this. 2 to the power of negative 2 is 0.25, sorry. 2 to the power of negative 1 is 0.5. 2 to the power of 0 is just 1. 2 to the power of 1 is 2. And 2 to the power of 2 is 4. So we can go ahead and graph these values. So here's 0, comma 1. There is 1, comma 2. Here is 2, comma 4. And we'll go ahead and try to graph these ones as best we can. We can then graph what this curve is going to look like. And you try to do as best you can because, if you're in a pencil here, it's kind of tough. So you just kind of put arrows on the end of it and you end up getting this J curve, which looks exactly the same as the one we had previously, just has a different scale. And so the only thing we do now is we politely write that this is f of x is equal to 2 to the power of x. So the inverse, which will be f of negative 1, all we need to do for this one is we just take our x and y values and just swap them over. Okay, so here we're going to have 0.25 and negative 2, 0.5 and negative 1, 1 goes to 0, 2 goes to 1, and 4 goes to 2. And all I did was read the values from above and just swap their positions. So 4, comma 2 would be here, 2, comma 1 would be here, there's 1, comma 0, 0.5, comma negative 1 is about here, and there's our last value. And so again, and I gave us one bonus one before, so let's go type that one in. And we can connect these with a smooth curve. And so this is the inverse function. X is equal to 2 to the power of y. Okay, so we're easily able to get the inverse by just graphing the original function and then swapping the position of our x and y values. Okay, let us continue on. oh no, we're close, pretty close to done here. And so the only thing I want to mention about this is that I want to use the idea of this exponential inverse in order to go ahead and solve these. So I'm going to try out, say, one more example for us. So we're going to say graph y is equal to 3 to the power of x and its inverse. Okay. So again, the way to do that is we take our normal coordinates, say x comma y, and we choose just the regular values. So let's say -3, -2, -1, 0, 1, 2, and 3. And so you evaluate each of these points, each of these y coordinates at the given value. So we're going to be typing into our calculator 3 to the power of -3, then 3 to the power of -2, 3 to the power of -1, 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, and 3 to the power of 3. And again, when you're just typing these into your calculator, just again, practice typing them in as is. So this 3 to the power of -3 is equal to some awful decimal. So we know that it's really supposed to be 1 over 27. Might be hard to type in, so for our purposes, we'll just put in 0.04. 3 to the power of -2 is going to be 0.11. 3 to the power of -1 is going to be 0.33. 3 to the power of 0 is just 1. 3 to the power of 1 is 3. 3 to the power of 2 is 9. And 3 to the power of 3 is 27. So this is what we would call the original function. The inverse we can get by just swapping the x and y values. Okay? So our x and y, or if you prefer, you could say y is our inverse, like that's fine as well. So for x value, we're going to end up with 0.04, and that goes to -3. 0.11 goes to -2. 0.33 goes to -1. 1 goes to 0. 3 goes to 1. 9 goes to 2. And 27 goes to 3. And all I did was swap these. So if I had x comma y over here, they turned into y comma x over on this side. And so when you graph these ones, they will have this particular shape, these J curves. It's worth noting that these J curves all kind of look like, will have this shape. And on the lesson of next time, what we'll start off with will be a warm-up question where it'll have this line of reflection business, but it'll be a slightly different shape because we're going to have a base value that's not going to be 2 or 3. It'll actually be a fraction. But for now, I think that's a good place to stop. And we'll see all of you on the lesson of next time.